This lab will build off of Lab 1 by using the interactions of two identically charged pieces of tape in order to determine the amount of excess charge on each one. Previously, we used a simplified model of the tape by representing both as 2-point charges, but in this lab we will instead represent them as lines of charges, which will more accurately reflect their real charge distributions. Additionally, in Lab 2, similarly to Lab 1, we'll explore the concepts of charge conductors and insulators. However, this time we will also begin discussing charge distribution and how net charge is composed of much smaller charge particles. Using these principles, we will construct a model that represents a strip of positively charged tape exerting a force on another identical strip such that the latter one is suspended in midair in equilibrium. Using this model, you will see that we can successfully approximate the amount of charge on a strip of tape to be about 1.3778 times 10 to the negative 8 coulombs. The first principle we will discuss is charge. Charge is a fundamental quality that causes objects to experience a force while in an electric field. Charges can either be positive or negative, which will determine the direction of their acceleration in the electric field. We will also consider charge distribution. While any object may have an overall net charge, this net charge is actually composed by a number of smaller charge particles distributed throughout said object. Assuming uniform charge density, a one-dimensional uniform charge density, lambda, is net charge over length. A two-dimensional one, sigma, is net charge over area, and a three-dimensional one, rho, is net charge over volume. Conductors have many mobile electrons that will move in the opposite direction of the external electric field. As a result, the internal induced electric field has the same magnitude but opposite direction of the external electric field, such that the net internal electric field is zero at equilibrium. Insulators, like the plastic tape strips, are materials with few mobile electrons. When in an electric field, the electron clouds of the atoms are distorted, such that the induced dipole is in the same direction as the external electric field. However, you can still create a net charge in the insulator by using mechanical motion to remove some electrons. If you recall from the previous lab, we were able to create charged strips of tape through mechanical motion by tearing electrons from particles on the surface of the tape. Likewise, we were able to determine the sign of the charge on the tape to be positive based on its interactions with a negatively charged plastic pen. Thus, we can charge two identical pieces of tape, tape A and tape B. If we create a system with just tape B in it, suspended midair, and if we bring tape A in from the surroundings, then as soon as tape B begins to move, the force on tape A on tape B will be in equilibrium with tape B's own weight. This model is certainly flawed, and while we don't need to ignore the air resistance of the object since tape B's acceleration is zero, and nor are we still treating the two pieces of tape as point charges, we are still assuming that the U tapes have identical, evenly distributed charges, which isn't necessarily true. Representing the orientation of the tapes as line charges does not necessarily reflect that they have a three-dimensional aspect. In the code, we'll use a discrete representation of a line charge. Therefore, we can put an estimated charge as well as the tape's masses, separations, and lengths into our program. We will likely have to change the value on the charge so that the electrostatic force is in equilibrium with the weight. Using my code from Lab 0, I created a function to calculate the electric field due to a charged particle at a particular observation location. First, I calculate the displacement vector between the two by subtracting the charge position from the observation point. From there, I can also find the magnitude of this vector as well as the unit vector. I then plug these values into the definition of an electric field due to a point charge. Then use the included functions to create line charges to represent both pieces of tape. Each line is 20 centimeters long, and each tape has a mass of 0.0002 kilograms, and all of them have a net charge Q, as we initialized earlier. Playing around with the scale, I settled on a factor of 75 for the weight and electrostatic force, and then for the scale of the electric fields due to the dq charges, I used a scale of 5 times 10 raised to the negative 7. Then, in the nested for loops, the program iterates through each point charge in tape A, and for each charge in tape B, it calculates the electric field due to this small amount of charge, as well as the force at the charge in tape B. At the end, it will sum all of these forces up into one net force. From there, the program creates two arrows, one to represent the weight, which is just tape B's mass times the gravitational acceleration on Earth times negative y hat, as well as one that is just the scaled electrostatic force we calculated earlier. You can see in the terminal that the magnitude of these two values are printed out, and after some guessing and checking, I got that the excess charge on tape B was 1.3778 times 10 to the negative 8th coulomb. Think back to the original purpose of this lab, we successfully modeled the system using a line charge. Then using this model, we were able to successfully determine the excess charge to be around 1.3778 times 10 to the negative 8 coulombs. However, I should also point out that these results are still inaccurate, as like we discussed earlier, the charge distribution is not necessarily a line charge, and the values we measured from lab 1 are not perfectly accurate either due to human error. Using the point charge model, you could calculate that the amount of excess charge on the tape is about 4.67 times 10 to the negative 9th coulombs, which is an order of magnitude smaller than the charge that we calculated using this model, about 1.3778 times 10 to the negative 8th coulombs. This is due to the fact that in the point charge representation, all of the charge is concentrated at the center, while the line charge representation more accurately represents how the individual charges distributed interact with the many charges that make up the other piece of tape as well. Therefore, the line charge estimation is more accurate.